Hi, my name is Arun, and this talk will be presenting the paper Near Linear Time Edit Distance for indel channels, and this is based on joint work with Aaron Tsai. So most of you are already probably familiar with the edit distance problem, but let's just go ahead and recap it for completeness sake. So in the edit distance problem, we're given two strings S1 and S2, and the goal is to find the edit distance between them, which for this talk we'll define as the minimum number of substitutions, insertions, and deletions needed to change S1 into S2. So for example, if I have these two strings, then I can delete the first character, substitute this T for a C, and then insert a T at the end, and I get S2 from S1. So here the edit distance would be 3. Now, of course, there are generalizations of the edit distance problem, where we might assign substitutions, insertions, and deletions costs that aren't just 1, or we might have different costs for substituting in different characters. The results in this paper will generalize to a wide variety of these generalized costs, but just to simplify the presentation, I'm only considering the setting where each of them has cost 1. And of course, the edit distance problem has numerous applications in computational biology, and I believe probably the audience is much more familiar with many of these than I am, so I won't spend too much time on that here. So for the purposes of this talk, it's going to be easier to view the edit distance problem as a shortest path problem. So here we define the dependency graph as the grid of n1 by n2 vertices, where n1 and n2 are the lengths of the two strings. And our goal is to find the shortest path from 0, 0 to n1, n2. And we have every possible horizontal, vertical, and diagonal edge. And all the edges have cost 1, except for the diagonal edges that correspond to two matching characters. So for example, we have the same two strings as we did on the previous slide here. And if we look at what the shortest path in this graph is, the shortest path will be this one, which has weight 3. And that corresponds exactly to the 3 edits we saw in the last slide. So let's just briefly recap some of the past results on the problem. So of course, there's this textbook algorithm that can find the shortest path in n squared time. Now, if we know the edit distance is at most d, then we can ignore all the vertices whose indices differ by at least d. And so we'll be left with at most nd vertices, and so we can compute the shortest path in nd time. Now, what Landau-Myers-Schmidt showed is that if we're a bit smarter about how we set up our dp, then we can actually compute the edit distance in order n plus d squared time if we know the edit distance is at most d. And also, if we, even in the setting where d is something like order n, we can still get a subquadratic algorithm which runs in n squared over log squared n time. However, the trend you'll notice here is that for all of these, if d is like n, then all these run in basically n squared time. And this is for good reason. What was showed a few years ago is that assuming the strong exponential time hypothesis, there's no algorithm that runs in, say, n to the 1.99 time. So under this assumption, we can't hope to do better than quadratic. Now, of course, for many practical applications, especially in computational biology, quadratic is very impractical because we're dealing with strings that are millions to billions of characters long. So the natural question is, how do we get around this quadratic time barrier? So one approach in the theory community has been to define approximation algorithms. So for example, there's been a recent exciting line of work, which I believe the most recent result is a 3 approximation algorithm in roughly n to the 1.6 time. However, for biological applications, 3 approximations are usually insufficient, even though 3 seems like a small approximation ratio in most settings. And the reason for this is that even with a 3 approximation, you can't distinguish between two mammals being more closely related than, say, a mammal and a bird, for example. So since we can't hope to settle for approximation, another thing we could try to do is come up with average case analyses of edit distance. So there have been plenty of average case models studied with applications in file management in mind, but not that many with computational biology in mind. For example, one well-known average case result is that we can compute the edit distance between two compressible strings in time proportional to their length times their compression length rather than the length squared. However, the problem with applying this to biological applications, for example, is that in many biological applications, the strings don't compress by more than a constant that's not that large compared to their length. So in this talk, we'll study an average case model which does have computational biology applications in mind. So in this model, we'll generate a pair of strings. The first string will be generated uniformly at random from all bit strings of length n. And the second string will be generated by taking the first string, and for each bit, independently applying a substitution, a deletion, or an insertion to the right with some small constant probability. And in the paper, we actually consider a more general model where multiple bits can be inserted or deleted at once to represent splicing in, for example, entire sequences rather than just individual sites. However, for this talk, to keep things simple, we'll just consider splicing in one character at a time. And just to make you confident that I didn't pull this model out of thin air, this is very similar to the CFN model with insertions and deletions included. And the CFN model has been extensively studied in the context of phylogenetic reconstruction, for example. So the main result that we'll go over in this talk is that for two strings sampled from this model, we can compute the edit distance between them in n log n time with high probability, as long as each of the substitution, insertion, and deletion probabilities per bit are at most a certain small constant. Okay, so just to give you an overview of the talk, first I'll describe the entire algorithm at a high level, and it'll consist of two parts. The first will be finding an approximate alignment, and I'll go into the details of that. And then we also need to say why the rest of the algorithm is efficient, and I'll do some error analysis to conclude the talk. So let's just start with the high-level algorithm. So let's let A star denote the path in the dependency graph, corresponding to the set of mutations that actually happened when we were generating S1 and S2. Now it's important when defining A star to note that A star is not necessarily the optimal alignment. For example, if we're in the substitution-only case, with reasonable probability, we could get a dependency graph that looks like this. Now here, since we only have substitutions, the true quote-unquote alignment will only take diagonal edges, so I've highlighted here in bold. However, this is not the shortest path, because here it has length 3, whereas there is a path that has length 2. Okay, so letting A star again denote the sort of true alignment in the dependency graph. What we're going to do is let V star be the vertices in the dependency graph that are within distance k log n of A star. So for example, if this is my dependency graph and this is A star, then V star will just basically be the band of vertices within log n of A star. Okay, so then given this definition for V star, we claim that in near linear time, we can find a path A prime that is entirely contained within V star. And we also claim that with high probability, the shortest path in the dependency graph is going to be entirely contained within V star. So then our algorithm is basically just to find A prime. And then if we consider all the vertices within distance 2k log n of A prime, this will be a superset of V star, which means that the optimal alignment is contained within these vertices. And so we can just run the dynamic program on this set of vertices. And then this set of vertices will be of size n log n, so the entire thing will take n log n time. So now let's talk about how to find A prime, which again is just an alignment which is very close to the true alignment. So the primitive we're going to use to construct A prime is one which distinguishes between a certain index ij in the dp table being distance at most log n away from A star versus distance at least k log n, and we'll do this in log squared time. So how does the primitive work? So let's say we were trying to apply the primitive to index ij. So within S1, we're going to define the substring S1 prime, which is the k over 2 log n length substring starting at index I. And within S2, we're going to define S2 prime as the substring that is mapped to from S1 prime by the true alignment. In other words, S2 prime contains the characters in S1 prime after all the mutations have been applied to them, and it also includes, of course, all the bits that have been inserted by mutations within S1 prime. So as long as the mutation probabilities are sufficiently small constants, then the edit distance between S1 prime and S2 prime will be at most some constant times k log n with high probability. Okay, so let's say we are in the setting where j is at most log n indices away from where it should be. So really we want j to be at the leftmost index within S2 prime, but perhaps it's not too far away. And now let's call S2 double prime the length k over 2 log n substring starting at index j. So this S2 double prime, the difference between it and S2 prime will be these characters to the right, and the number of these characters will be at most log n, which is the shift on the left side, plus the difference between the number of insertions and deletions in S1 prime, and also, of course, these characters on the left side, which they're at most log n of. So if we apply triangle inequality, we'll see the distance between S2 prime and S2 double prime is just the lengths of these segments. And so triangle inequality says that the edit distance between S1 prime and S2 double prime is at most some small constant C1 times k log n with high probability. Okay, so this says that if I and j are close to A star, then we can just compute the edit distance between the length k over 2 log n substrings starting at indices I and j, and we'll get a small edit distance. So now we just need to show that if I and j are far from A star, that the edit distance will be large. And the idea is basically, since j is at least k log n away from where it should be mapped to, then S1 prime and S2 double prime are going to be completely disjoint substrings in the sense that none of the characters in S1 after insertions and deletions is put into a position contained within S2 double prime. So since they're independent random bit strings, it's well known that the edit distance between two random bit strings is with high probability at least some constant k log n. And if we set our mutation probabilities to be small enough, this constant will be larger than the C1 constant on the previous slide. So in other words, if ij is close to a star, the edit distance between s1 prime and s2 double prime will be small. And if ij is far enough away, it'll be large. And so this gives us this primitive. So given this primitive, what we're actually going to do is not construct an entire approximate alignment. Instead, what we call an approximate alignment is really going to be a set of points in the dp table, one for each I that's a multiple of k log n, such that each of these points is close to a star, as in within distance, say, k log n from a star. And this is efficient because if we take each of these points and we draw a box centered at that point with side length at least, say, 3k log n, then the union of these points contains v star, the set of vertices which is close to the true alignment, and which we know contains, with high probability, the optimal path. So given the approximate alignment, we can just take the union of these boxes and run the dp table on this union, and this will give us an n log n time algorithm. So we can always start off our approximate alignment with just the value 0, 0, because of course that's going to be exactly on a star. And now let's say after some number of iterations, we've extended our approximate alignment all the way to the point ij, and we're wondering what's the next point we should add. So in particular, we want to add some point of the form I plus k log n comma j prime. And the claim is that the only reasonable values for j prime are going to be within, say, 3k log n of whatever j is. That is, the next point we want to add is definitely contained within this vertical band of total length at most O log n. The reason for this claim is that in the indices I to I plus k log n of S1, only so many mutations can occur, and thus the value of j can only shift so much in this range. So given this claim, we also realize our primitive only needs us to be within distance log n for it to give us a small edit distance when we compute the edit distance between the substrings. So rather than try every value in this range, we can just try every log n value in this range. And we have the guarantee that one of these values, when we run the primitive on it, is going to give us a small edit distance. So this combined with the fact that if we pick a point too far away, the primitive will give us a large edit distance, tells us that if we just run the primitive on each of these points, look at the edit distances of the substrings we get from running the primitive, and then choose the point corresponding to the smallest edit distance, then that point will be close to a star. So how long will this take? Well, for each I, since we have a vertical band of length log n we're considering, and we run the primitive on every log n value, there's only a constant number of uses of the primitive for each value of I. Since we only look at every k log nth value of I, there's only n over log n I values, and then each use of the primitive costs log squared n time, so the total runtime is n log n as desired. So now that we know how to construct the approximate alignment, let's go into the error analysis, which says that the optimal path, the shortest path, must be close to a star, the true alignment. So for this part of the talk, just to simplify presentation, I'm going to consider the substitution only case. That is when the true alignment is just the diagonal. In the paper, we do extend this argument to the case with our insertions and deletions, but it requires some more technical detail that I don't have time for here. So the idea is, let's consider any path which leaves V star, the set of vertices near A star. Any such path contains a break, such as this one highlighted in red. And by break, I mean some maximal subpath within that path that is completely edge disjoint from A. And because this path leaves V star, the total number of insertions and deletions in the path must be at least k log n, and in particular, the total length of the path is, of course, at least k log n. Okay, so the idea is we can just use a turnoff bound to argue that basically every insertion and deletion on this path is going to contribute at least 1 to its cost. And it's possible to show that every diagonal edge on this path, the weight of that edge is a Bernoulli with parameter 1/2. And so a turnoff bound lets us show that with high probability, it's better to stay on the diagonal, because while here the diagonal edges have expected weight 1/2, if our substitution probability is small enough, here the diagonal edges are going to only have some small expected weights. So a turnoff bound says something like, for any path with a break from A star of length at least k log n, with probability at most n to the minus k, it's better to just stay on the diagonal. So what we like to do is then just take a union bound over all such paths that leave V star. The problem is there are many such paths, because we can always just introduce a tiny break, for example, to get a basically identical path, but this still contributes an extra path to our union bound argument. So we need to do something a bit more clever in terms of how we bundle the paths for our argument using a union bound. So to do this, let me just introduce some notation at first, and then I'll explain later why this notation is useful for this argument. So given any path A, let me define L of A to be the same path, except we take all breaks of total length at least k log n and replace them with the diagonal. So here A has this long break, and when I apply L to A, I get the same path, but with this break replaced with a diagonal. So our goal, just the exact same goal from the previous slide, is basically just show that any A is worse than L of A, because L of A is going to be contained within the part of the DP table that we search. So if we can show this is true, then we know our algorithm is correct. So given this goal, I'm going to define some more notation. So similarly to L of A, let S of A be A with all breaks of size less than k log n replaced. So remember, in L of A, we replaced the long breaks. In S of A, we're replacing the short breaks. So the reason defining S of A is useful is that A is worse than L of A if and only if S of A is worse than A star. Because if you look at the difference between A and L of A versus the difference between SA and A star, it's the exact same difference. These two are, A and L of A are paying the exact same cost for this segment. The only segment where the cost differs is here, and that's the exact same segment where SA and A star differ. So given this observation, I can replace my goal of showing that any A is worse than its corresponding L of A with an identical goal, which is show any alignment in the range of S is worse than A star. And the reason this is nice is that the range of S is much tinier than the set of all alignments. So hopefully now I can make this union bound argument work. So I want to show that any alignment in the range of S is worse than A star. So I can use a counting argument to show that there are roughly n to the I alignments in the range of S with total break length I k times log n. And remember, this wasn't possible before because we could always make tiny variations to alignments that didn't really affect them, but that really arbitrarily increased the total set of alignments there were. But now I'm in the range of S where I'm only allowed to make large variations from A star, so it's no longer to make these tiny adjustments. So then we just recall from before that for any alignment with total break length at least ik log n, with probability n to the omega ik, it's better to stay on the diagonal. And now if I combine these two observations and k is large enough, then a union bound gives me exactly this goal that any alignment in the range of S is worse than A star. Okay, so this concludes the error analysis. So let me just finish by discussing some possible future directions. So one thing that is not clear is whether n log n is the best that one can possibly do in this setting. Intuitively, it feels like it should be the best possible because that primitive we had of comparing substrings of length log n, if we go down to say substrings of length squared log n, it's not clear necessarily why that primitive should work, but there's no information theoretic argument we know of to justify n log n being the best possible. In addition, throughout the talk, we assumed that the mutation probabilities were at most a certain small constant. However, we didn't bother to optimize what that constant was. So in the paper, we tolerate something like a mutation rate of, say, 5%. Obviously, in many applications, we'd want to tolerate higher percentages. And again, we have no formal reason to believe that 5% is the best we can do. So optimizing the mutation rate would be an interesting future direction. In particular, in other settings where we study similar models, such as phylogenetic reconstruction, it's known that sort of the mutation probability undergoes a phase transition, where the problem is efficiently solvable as long as the probability lies within some range, and then the problem becomes intractable or information theoretically difficult when the probability enters a larger constant range. So it'd be interesting to say something like, if the mutation probabilities are at most C, then we can find the edit distance at n log n time, and then maybe past that we need something like n to the log squared n or n squared time instead. Finally, it will of course be interesting to consider other average case models that maybe capture aspects of actual biological applications that our model failed to cover, and see if we can get fast edit distance algorithms for these models, and hopefully bring the results in theory closer to the actual applications in practice. All right, that concludes the talk. Thank you so much, and I'm very happy to answer any questions in the live session.